And we're back. We were talking about the predator-prey model, but you'll notice that this system looks amazingly like a matrix system. In fact, if I let the x vector be f sub k and r sub k, the number of foxes at time k and the number of rabbits at time k, and x sub k plus 1 be the number of foxes at time k plus 1 and rabbits at time k plus 1, and if I let A be the coefficient matrix here, then this reduces to, or could be written as, x sub k plus 1 is A times x sub k. So whatever we get out for the one step then goes back in and will give us the next step and the next step and the next step and the next step. And so we take our steps in cycles here using our A matrix. So let's go ahead and analyze this A matrix. And we're going to let you do a little bit of practice here. I want you to find the eigenvalues and eigenvectors for this A matrix, and we'll pause our video and pick up when you've done that. Okay, now that you've had a chance to find the eigenvalues and eigenvectors, you should have found that one of the eigenvalues is 1 with corresponding eigenvector of 1, 2. And the other eigenvalue is 0.6 or 3/5 with corresponding eigenvector 3, 2. Now, something to note, if x sub 2 is equal to A times x sub 1, and if we wanted to find then the next step, x sub 3 would be A times x sub 2, oh, and these are vectors. Well, that would be A times x sub 1. Or in other words, A squared x sub 1. So you can see why finding powers of the matrix can be very helpful. So if I wanted to find x sub k plus 1, I would then find a to the kth power times x to the first power. So let's go ahead and put our matrix in, our A matrix into the calculator. And let's start out, or suppose that we start out with 10 foxes and 50 rabbits and see what happens. So I'm going to put A matrix in as 0.4, 0.3, negative 0.4, and 1.2. And I'm going to put the B matrix in as a column that is 10, 50. So a 2-by-1 matrix. So let's go ahead and do that. Hang on a second. I think I just had a technical difficulty there. So we're going to put in the A matrix and the B matrix into the calculator. And actually, I'm going to start out at x sub 0. So if I start out at x sub 0, then x sub k plus 1 would be A to the k plus 1 times x sub 0. So what we're going to do is we're going to use this matrix to transition from the 0th state, starting state, to the first time period, second time period, third time period, 8th time period. And let's use some technology to do that. All right, so I have this in as my A matrix, that in as my B matrix. You can see that here on my calculator. And if I avoid the glare, x sub 1 would be A times B, which would be, let's go ahead and calculate that with our calculator. It's going to be 19 and 56. So we'll see that the number of foxes jumped quite a bit because there was plenty of rabbits to eat, and the number of rabbits increased a bit as well. Okay, so let's find x sub 2 by multiplying this by A, and what I can do is I can use the answer feature on my calculator to do matrix A times the answer matrix, the previous answer, and we'll find out that this is going to give us 24.4 and 59.6. Obviously, you can't have 4 tenths of a fox or 6 tenths of a rabbit. but you kind of get a feel for what we're modeling here with our rabbits. So we have about 24 foxes and about 60 rabbits now. Let's go ahead and do that again. So x sub 3 would be 27.64 and 61.76. Okay, so about 28 foxes and 62 rabbits-ish. Okay, x sub 4. At the fourth time period, we're going to have, I'll round to 2 decimal places, 29.58 and 63.06. So we did have some big jumps early on, but now the changes are getting smaller. So x sub 5 is 30.75 and 63.83. Yeah, those changes are getting a lot smaller, aren't they? So it looks like we're coming to what we would call an equilibrium solution. Let's find out what that might look like. So 31.45 and 64.30. 31.87 and 64.58. And finally, x sub 8 is going to be, let's see if I can weasel this on the page there. So 32.12 and 64.75. So it looks like, at least in this scenario, things are getting pretty close to an equilibrium solution. In fact, I'd like you to take and use powers of the matrix, and let's find x sub 20, x sub 40, and x sub 100. We'll go ahead and use technology for that. So let's see what we get. Well, if we do 20 time periods, we get rounded to 2 decimal places, 32.5 and 65. And at 40 time periods, we're getting 32.5. Wow. Rounded even out way out here, 32.5 and 65. And if we do a to the 100th power, times matrix B, we get 32.5 and 65 exactly. So we are heading to an equilibrium solution. And notice that if I were to factor out the 32.5 from that equilibrium solution, so I know we can't have half a fox, but this is a relationship here. So we have a 1-to-2 relationship of the number of foxes to the number of rabbits. And if you're careful, you'll notice that that corresponds to the eigenvector corresponding to lambda equals 1. And notice that when we were to do the powers of the A matrix, we're going to get some diagonal matrix to that kth power. And when we do that diagonal matrix to the kth power, we're going to have 1 to the kth power and 0.6 to the kth power. So this guy right here, the 0.6 to the kth power, as k gets bigger and bigger and bigger, we're getting 6/10 of 6/10 of 6/10 of 6/10. That is going to go to 0, and we'll get 1, 0, 0, 0 when we're doing that guy. So that's why this guy actually looks a lot like this eigenvector rather than that eigenvector. Okay. Hopefully that's made sense. Now go try the homework and let me know if you have any questions.